everyone. The last video that we talked about, we were talking about calorimeters. And in calorimeters, focusing on bond calorimetry and coffee cup calorimetry. And with coffee cup calorimetry, that's the one we're going to spend most of our time in because we're not going to be doing things in a closed container like in a bomb calorimeter where there is no work. So we're going to be focusing on Q, and remember that Q sub P, Q at constant pressure, is equal to delta H. And so we're going to talk about ways that we could find Q. So there are some equations to know that should look familiar to you. From Chem 1. So one of those is Q is equal to, in Chem 1, you probably learned it as SM delta T, Q SMAT, as many of you did. You're going to find your book does not use S, but in fact uses C, M delta T. So don't be confused. In both of these cases, C or S, it's referring to the specific heat capacity. So specific heat capacity tells us something about how a substance gains energy. So as an example, the specific heat capacity for liquid water is, and you should memorize this one, 4, but not when I write it wrong. Don't memorize it wrong. 4.184 joules per gram degree Celsius. So what that means is that it takes 4.184 joules of energy, remember joules and energy, to raise 1 gram of water 1 degree Celsius. That tells you how much energy it takes. As an example, aluminum has a specific heat capacity of 0.897 joules per gram degree Celsius. So you can see it takes a lot less energy for aluminum to raise its temperature than water. So back to this, Cm delta T. Some people like to remember it as Mc delta T, MCat, whatever you like. But one thing that is important to know is that delta T is always defined to be T final minus T initial. And that's important for you to understand, that we always do final temperature minus initial temperature. It allows all those signs that we have talked about before, the pluses and minuses, to be accurate for Q. So that's one of the equations that we need to know. Second equation, negative Q lost is equal to Q gain. So if something loses energy, then something else will gain it, and they're going to be equal and opposite in sign, because whoever loses energy is automatically a negative. So if we take a negative of a negative, we're going to get a positive value. So that will be an important equation. And then a third equation, this isn't truly an equation as much, but it's related to that, is understanding delta H of FUS, which is fusion, as compared to delta H of VAP, vaporization. So heat of fusion is something that we use when we're going from a solid to a liquid, or a liquid back to a solid, either way. And just to give you an idea, the heat of fusion, sorry, I know you can hear all those clicks, is 6.01 kilojoules per mole. Or you might find it in your book as 334 joules per gram. So what that literally means is it takes 6.01 kilojoules of energy to melt a mole of ice. Or 6.01 kilojoules of energy is how much energy is released to freeze a mole of liquid water. The one thing we have to understand, though, is that these values, because you can look these up in a table, don't account for the signs, positive or negative. So if I'm going from solid to liquid, I have to put energy in, then my delta H of fusion is essentially positive 6.01 kilojoules per mole. But if I'm going from liquid to solid, it has to release that amount of energy. So it's negative 6.01 kilojoules per mole is the change in delta H for that. Like it's 6.01 kilojoules a mole per mole is released. Delta H of vaporization is what we use for liquid going to gas or back again. And for water, the delta H of vaporization for water, just as a comparison, is 40.7 kilojoules per mole. And again, that's how much energy it takes to go from liquid to gas, so positive, or how much energy is released when we condense gas to liquid, and so then that would be a negative number. How these numbers would get used is if I know that I've got, 2 moles of water that are condensing, then I can take my 2 moles of water, and if it's condensing, that's energy given off. The negative 40.7 kilojoules of energy will be given off per mole, and moles cancel, and I, get negative, 81.4 kilojoules being given off. So that would be a way that you could use that. All right, 3 types of problems that we may encounter. I'm going to go through them fairly quickly because several of these are review. You'll read about these in your book. So one of these is a heating curve problem. So an example of a heating curve problem might be how much energy is required to raise, that doesn't look like raise, but it's supposed to eat. Let's just start again. Raise the temperature of 100 grams of water from negative 30 degrees Celsius to 97 degrees Celsius. So this is a kind of a problem. And this is where you've seen this kind of a graph known as a heating curve, which is why I labeled it, where this is temperature and say this is 0 degrees Celsius and this is 100 degrees Celsius over, versus time. And you're starting here at negative 30 and you want to go up here to 97 degrees Celsius. And so the key thing in a problem like this is that anywhere you're on a diagonal, you have a temperature change. And when you have a temperature change, you use the equation Q is equal to Cm delta T. So I would use Q equals Cm delta T for this region. This little region here, I would use Q is equal to Cm delta T. Incidentally, this is water. So this C is 4.184 joules per gram degree Celsius. The specific heat of ice is slightly different. It's listed in your book. I don't have that one memorized, and I don't expect you to either. So you could find out how much, let's get a different color, heat energy it takes to go from, in this case, 0 to 97. That would be your temperature change, and your mass is 100. Here you're going from negative 30 up to 0. So 0 minus negative 30 is your temperature change, 100 grams. Then this area, however, there's no temperature change because here is where it's melting. That's a phase change, so that's where we're going to use delta H of FUS. And so in this case, I have 100 grams of water. I could change it to moles and use the moles one, or I can use the 334 joules per gram. Either way is fine, but that will tell me how much energy is used here. So I will have an answer to this, an answer to this, and an answer to this. I just need to make sure all of those are in the same units, and then I'm going to add them together. All right. Number 2, calorimetry. So here's a typical question. You have your little coffee cup calorimeter. Let's say it has 100 grams of water. It's 20 degrees Celsius. So cool water. Let's say that you have a piece of aluminum and it's hot aluminum, and you put that hot aluminum in the cold water. So of course, the aluminum cools down and the water warms up. Well, we know that negative Q lost is equal to Q gained. We know that negative Q for the aluminum, who's losing the heat, is equal to Q for the water. And so we know that negative 0.897 joules per gram degree Celsius. Oops, I skipped a step. Here, me write the formula. I'm jumping ahead without bothering to write it for you. I should write it for you. Q is Cm delta T. So negative C of the aluminum, mass of the aluminum, times delta T of the aluminum is equal to Q for the water, which is Cm delta T for the water. So C of the water, mass of the water, delta T of the water. So I plug in my numbers here. Oh, I didn't tell you, this is a 10-gram piece of aluminum. So 10 grams of aluminum times my temperature change, T sub F minus 80. I don't know what T sub F is. Trying to figure out what temperature will it end up at, is equal to 4.184 joules per gram degree Celsius times 100 grams times, the same temperature, T sub F minus 20. And now I play the fun with algebra game. They end up at the same temperature, so I solve it and find T sub F, which is my answer. The last kind of question, but I won't go through, but we will eventually, is that we're going to run into heat of reaction problems, like knowing what is delta H when a reaction happens. And that's something that we're going to take a look at